Hello everyone. So again welcome back to the latest lecture session, and obviously we are going to continue from where we left off, that is with respect to the applications of precipitation and dissolution. At least I tried to illustrate, I guess, with respect at least coagulation and flocculation, the different roles that Fe3 plus can play and Fe2 plus can play, right? And we discussed, I think, charge neutralization and the relevant effects, as in why Fe2 plus would be more effective there, right? Because it's mostly in the soluble form and stays as Fe2 plus. So the net positive charge would be greater when you add Fe2 plus. So if charge neutralization is the relevant aspect that you are mechanism for coagulation that you are looking for, so choosing Fe2 plus might be a better way to go about your coagulation, or more efficient way obviously. But if you are looking at forming sweep flock or co-precipitation, so obviously choosing Fe3 plus is the much better option. Why is that? Because you know that at pH 7, obviously, as you notice that Fe2 plus does not precipitate out, right, which is essential for, I think, the sweep flock or the co-precipitation. So again, what are some of the other aspects that you might look at? So one case we looked at until now were with respect to application of precipitation. So where do you think you might need to look at dissolution, let's say? So I guess the aspects would be that, let's say, you have contaminated soil with some precipitate of the relevant heavy metal on it, right? Let's say the heavy metal precipitated out and it's contaminating the soil now, right? It's not in the soluble phase. So in that case, you want to either change the pH or affect the ligand concentration, right, so that you make the compound more soluble, and then you can either by washing or relevant techniques, you can remove that particular heavy metal from the soil, right? That's one particular case. And obviously when you have what we say evaporative cooling towers, right, you have scaling formation, and let's say you want to remove them, again that's one particular case where you would want to look at dissolution again, right? Over time you would have scales formed on these particular evaporative cooling towers that people look at in the thermal power plants, right? And again, let's say in membranes, let's say, right? So you have scaling, not irreversible, I guess. There are reasons why people call them irreversible or reversible scaling. Irreversible as in under most chemical conditions you can't remove that particular scale or the solid, as in what does that mean? So that particular solid is remarkably insoluble. So even with change in the conditions with respect to pH or any other compounds that you add, you can't make it soluble. But reversible scaling, let's say, right, you can change the relevant parameters or chemical water quality parameters, let's say, or add different compounds to make the compound more soluble, right? So again, membranes over time, let's say membranes, we use them in what do we say, physical process based removal of contaminants, right, or particles, let's say. It's obviously depend upon the principle of size exclusion, right? Again, so thus at the surface of your particular membrane where the concentration of the relevant compounds are very high, you will obviously have, what is it now, conditions that favor the precipitation. As in, let me just try to plug this in. Let's say if this is my membrane here, let's say, anyway I will just use this, and let's say this is the flow of the water, let's say, right? So obviously near this particular membrane, right, the concentration of the relevant compounds will be remarkably high compared to what they would be in the bulk solution, right? So obviously if you have remarkably high concentration of the relevant let's say electron poor and electron rich compounds, you have favorable conditions for forming a precipitate, right? So but obviously that will lead to what we say decrease in the efficiency of your filtration, or the life of your membrane. So you need to remove that particular scaling from this particular surface of your membrane now, right? So there you look at the applications of dissolution, right? So again, so let's be done with let's say applications of precipitation and dissolution. I guess they are ever present, right? Let's move on from that. So now we are going to look at the other aspect, as in kinetics, I guess, right? So what have we been discussing with respect to each and every case thus far? Acids and bases, we discussed only equilibrium, right, not kinetics. Why is that? Because the kinetics are very fast in acids and bases, and in aqueous complexes too we mostly only consider, not mostly, we only considered equilibrium, because again, why is that? The kinetics are relatively fast, maybe not as fast as the acid and base reactions, but still they are fast enough, the aqueous complex based relevant reactions, so that most conditions in your practical scenarios you would end up reaching equilibrium, right. But with respect to precipitation though, right, that's not the case though. The kinetics they are slow or pretty slow depending on the type of compound that you look at and the type of solid that you are considering. So kinetics plays a remarkably important role in our particular precipitation related aspects. So obviously we need to consider the relevant rates of this formation of the precipitate or the formation of the solid and so on. So we are going to spend some time with respect to kinetics in this particular precipitation related aspects, and then look at obviously once equilibrium is reached, what are we going to look at. So obviously in precipitation we are going to discuss both precipitation and kinetics and equilibrium. Why is that? Again, kinetics is relatively slow with respect to the precipitation relevant reactions, right. So again now let us say kinetics again, why is this important now, right, in this case. So first there are different stages before you know, or not before, let us say during the formation of the solid. So let us say if you want to promote precipitation, you know, you need to consider the rate at which all these stages proceed. So that is something we are going to consider, but that is later though. More importantly though, you need to also look at the type of solid that is being formed. Let us see, if you remember that when we looked at the example in Tech, let us say with Fe2 plus or Fe3 plus, right, and we had to choose the type of solid phase that was feasible. We came across for Fe2 plus I think two forms, amorphous, right, I think of FeOH twice, and also the same molecular formula crystalline, right. And let us just to refresh our memory, let us go back there and look at Tech, I guess. So let us say I choose Fe2 plus 2 B, C, D, F, add to the list, and I am going to remove or delete Fe3 plus, right, back to main menu, and I am just trying to point out to you what are the different solid phases possible, and so I am limiting it to those species that can be formed only if Fe2 plus is present. So here you see that two forms are feasible. What is that now? Amorphous and crystalline, right. So that is one particular aspect, so keep that in mind please. And now let us say if Fe3 plus is considered, Fe3 plus let us say, add to the list, and I am going to delete Fe2 plus now. Again, what are we trying to do? We are trying to demonstrate what are the different possible solid phases. For Fe3 plus though, we have different kinds of types of solids present, ferrihydrate, hydrite, I mean there is something certainly with respect to amorphous and crystalline form and so on, right. So why do I need to know what kind of solid is prevalent or predominant in my particular solution now? Because if you look at the relevant equation, right, what is the relevant equation here? So let us say I have FeOH thrice, right, solid, and the relevant Fe3 plus and 3OH minus, right. So again the key is with the same molecular formula or slight variations we can have different types of solid, right. So the key is why do I need to look at this particular aspect now, right, because for each different type of solid I will have a different equilibrium constant now. Let us say K1 for one type of solid, K2 for solid type 2 and so on. So what is K1, or you know, it is the solubility product here. So the precipitation dissolution reactions usually we write it in the form of the solid dissolving into the relevant cations and anions, keep that in mind, and the relevant equilibrium constant we call that the solubility product. So Ksp1 and Ksp2 let us say for solid 1 and solid 2, right. So here obviously let us say what is this going to be equal to? Activity of Fe3 plus and activity of OH minus cube by activity of the solid, which is, as you know, activity of solid is 1, right. And again here again in the second case Fe3 plus and again OH minus cube by activity of FeOH thrice the relevant solid, but again as we know activity of the pure solid it is 1, right, the reference state, right. So again why is this important now? As you see the relevant concentration of the metal or the ligand, right, that is going to be present in your solution is dependent upon the type of solid, as in because Ksp1 is different from Ksp2, in this case I will have one concentration of Fe3 plus and here I will have a different concentration of Fe3 plus, right. So I need to know or identify what is the solid that is going to be present in my solution at this time that I am looking at it, right, because that will obviously control my particular metal concentration. So obviously what is it we need to identify? We always need to identify the controlling solid, right. So whenever we are looking at precipitation, so you need to ask the relevant person, so what is the possible solid, or what is the solid that you expect to be the controlling solid, as in there are many forms of solid, but only one would be the controlling solid. And why is that? Because based on knowledge from that controlling solid, you can get the knowledge with respect to the concentration of the relevant dissolved metals or ligands, right. So obviously you need to identify that particular controlling solid. So again, before we go further, how can we identify controlling solid? Now in general, let us say as we know from our particular background with respect to your Gibbs energy or free Gibbs energy and such, right. So in general, what is it that the system would drive towards or tend to move towards when the Gibbs energy of the mixture is minimum, right? Yes. Or if you are trying to look at it from delta G naught point of view, when even delta G naught is relatively less, right. So we are going to, the system is going to move in such a way that the Gibbs energy of the mixture is going to be minimum. So in which case will that be minimum now, right? So let us look at that. So here I have an example, I guess, again with respect to based on Al3 plus precipitation out. So here we have different forms of Al3 plus, right. These are all solids, keep in mind, okay, amorphous, boehmite, gibbsite of Al3 plus. So keep in mind that now again log K values are given here 10.8, 8.6 and 7.7, right. I think these are from VMITech, yes. So what is it that this tells you about the system now? So let us say if I add aluminum to a particular solution, from looking at or observing and analyzing the relevant K values or log K values, you can understand which is the solid that is going to precipitate out first. Obviously as we say now, let us say initially, let us say Gibbs energy of the system when I added Al3 plus is say relatively high, right, and it wants to travel down the ladder, right, it wants to reach equilibrium, right, as in the Gibbs energy of the system needs to keep falling now, right. So let us say this is the minimum Gibbs energy that's of the system that's possible now, right. This is just for your nomenclature. Initially we are here and this is the minimum feasible for that particular mixture. So where does the system want to travel? From here to here, but obviously there are different stages here. So the first stage will be when, in this case obviously because you look at the log K value that's higher, right. So initially you will come across the amorphous form, right, and then you will come across the boehmite form, right, and then you will reach the gibbsite form where looks like you are going to have the minimum Gibbs energy of your system, right. So initially let us say what is it that I am trying to help you visualize or understand. Here I am putting in Al3 plus, let us say, right, where we say in general the Gibbs energy of the system is relatively high, as in why does the compound want to precipitate out? Because every reaction wants to lead to such a system where the Gibbs energy of the mixture is relatively less, right. So obviously here as you see we are trying to move towards a more stable system. So initially the system is not stable, and as we are representing in this particular manner, right. So next it will move to the next feasible stable form, which initially would be amorphous, right, and then it would move on to the boehmite and then to the gibbsite, right. And obviously you can look at that or understand that from the log K values. The log K is highest for your particular amorphous form. What does that mean now? So as in AlOH thrice solid. Anyway, whenever we write log K values, this is the equation we are talking about, as in the solid dissolving into the relevant cations and anions, right, 3 OH minus, right. So what does this mean now? Log K is relatively higher for this particular equation, as in what does that mean? So as you know, K is equal to the activity of Al3 plus times the activity of OH minus cube. So the greater the K, what does that mean? In effect, for certain pH or fixed pH, it means the greater the concentration of Al3 plus, right. So from this again you can understand that the amorphous form is soluble, but this is relatively insoluble or relatively insoluble, I will call that insoluble compared to amorphous, the Boehmite form. Why is that? Log K value is less. So, if log K value is less, what does that mean? The Al3 plus concentration in solution at equilibrium is also going to be relatively less compared to the amorphous form, right. I will try to illustrate that in a better manner again. So, compared to amorphous form, the Boehmite is relatively insoluble, again obviously with respect to Al3 plus, and again Gibbsite is the insoluble form or the most insoluble form, and you can understand that from the lowest possible value for this particular aluminum relevant what do we say precipitates, which is 7.7, right. So, again let us try to plug this in somewhere here. So, let us say the relevant form for AlOH thrice, right, solid, and that can go to Al3 plus OH minus, right, 3 OH minus. So, the log or K value is going to be equal to the activity of Al3 plus times OH minus cube, right. So, a higher K as in amorphous form, what does that mean? It translates to a higher value of Al3 plus that will be in solution with the solid, not solution, pardon me, in equilibrium with the solid. As in, keep in mind, obviously you are also going to have some metal in the form of the dissolved phase, and that is going to be in equilibrium with your solid here, right. So, again what was the example we looked at? We came down the ladder. Initially let us say Al3 plus, right. The next possible form was the first solid that we formed, amorphous form, that was the amorphous form is formed first, and next we will form the relatively insoluble form of Al3 plus, that is Boehmite, right, and next we will see the Gibbsite, and obviously as you see what is happening with respect to log K value 2, that is decreasing, right. So, again as K keeps decreasing, you see that Al3 plus concentration 2 keeps decreasing, yes. So, what does that mean? That means when Gibbsite is the predominant or controlling solid, the Al3 plus concentration would be the minimum compared to the other two cases, right. So, again that is what we are trying to understand here, and that is why you need to know the controlling solid. As in, why is that? Let us say people think that Gibbsite is the controlling solid when actually amorphous form is the controlling solid. What will it lead to? See that the difference in log K values is 3 orders of magnitude, right, or 3 I guess, 10.8 and 7.7 or 7.8. So, the difference in log K is 3, right. So, as in K would be differing by 10 power 3, yes. So, your aluminum concentration would be lower by 10 power 3 if you choose Gibbsite compared to if you choose amorphous, right. So, if you incorrectly identified Gibbsite as your controlling solid, you would assume, or from your calculations, that the aluminum concentration is 10 power 3 times lower than what is actually present if let us say amorphous form is the controlling solid, right. So, that is what we can understand here, and obviously as you go down from this particular ladder, the Al3 plus that is present in equilibrium with the solid in this case is amorphous, in this case Boehmite and Gibbsite, the Al3 plus concentration 2 will obviously keep decreasing, right. So, that is one particular case. So, what is it that you can understand from here? The most soluble form of the solid will be formed first, and the least soluble form of the solid will be formed last, right. So, the thermodynamically what is favored now, as in G of the mixture should be minimum, or delta G should be also relatively less, right, delta G naught anyway, not delta G, pardon me. As you remember, delta G naught, how can you get that? Equal to minus RT natural logarithm of K. Again, so when will that particular aspect be favored? Obviously, again only when what is this now, log K values are lower, yes, and that is what we observe here. So, again what is it that we are trying to say again? Let us summarize here. So, the controlling solid is important because that drives the concentration of the metal or the ligand that is going to be present in your solution, that is one aspect. And secondly, when we are looking at which forms first, the most soluble form would be formed first, right, as in first amorphous form will be formed first. Al3 plus can't directly jump to Boehmite, first it will form the amorphous, then it transforms into Boehmite, and then it transforms into Gibbsite. So, last would be the form that would be the most insoluble, right. So this is the most insoluble and this is the relatively more soluble, right. So first amorphous is formed and last Gibbsite is formed. Let us just try to understand that here. So I guess with respect to Fe3 plus, right, and we have different forms, one is ferrihydride aged and goethite and ending up with hematite, right. So here from our background, what is it, which form will be formed first now? I need to look at the log K values, right. So this is okay, again 6.836 and 3.193, I guess the different conditions. So minus 4, if I neglect this, let us say for now, so I see that it is in a decreasing order, right, the log K is in decreasing order. So what is it that we know? Ferrihydride is the more soluble form of the solid. Why do I call that the more soluble form? Because FeOH thrice, the solid is in equilibrium with Fe3 plus and 3OH minus, right. The greater the log K value, the greater the Fe3 plus concentration that is in equilibrium with the particular solid, right. And the lower the log K value, obviously the Fe3 plus concentration in equilibrium with the solid is going to be lower and lower. So that is why I call ferrihydride the relatively more soluble form and hematite the most insoluble form, right. Why is that? Again, as you see, the log K value is remarkably low, right. So obviously what can you understand now? First ferrihydride will be formed and then ferrihydride the aged form is going to be formed and then lepidocrocite, I guess, goethite and then hematite, right. So it is going to go in those stages, and obviously again I need to identify which particular solid is the controlling solid. Why is that? Again, only from that can I know what is the log K value, and depending on that I can understand what the particular Fe3 plus concentration is, right. So that is something that we can look at here, let us say. Okay. So let us look at what it is that we are trying to represent here. Here we have a graph with concentration and time. So this is the concentration of, let us say, your particular what do we say, metal, let us say, and so that is keeping on decreasing, right. So let us say this is the true equilibrium, right, this is the true equilibrium, and at the true equilibrium what is going to be formed? The most stable form, the most stable form. And what is the most stable form? It is the least soluble or the insoluble solid, right, insoluble solid. So at the, when the true equilibrium is reached, what is it that we have? We have the most insoluble or the least soluble form, solid, pardon me, this is the solid, right. So here it is truly stable, and as in one example is that it will be the least soluble crystalline solid, right. So what will be formed first? Here we have two different kinds of equilibriums here. One would be the metastable equilibrium, I guess, right. So for practical cases it might look like we reached equilibrium, but that is not the true equilibrium. The changes are so infinitesimal or relatively small that it appears as if you reached equilibrium. So I am going to call that the metastable equilibrium. So first stage, what am I going to form? As we looked at earlier, we are going to form the amorphous form of the solid, right. When the solid has PHOUS, right, amorphous form of the solid. Right. So this obviously is the most soluble solid, right. And next stage, what would that be again? This is again metastable equilibrium, and here I am going to have a crystalline solid, but it is going to be a soluble form of the crystalline solid. So obviously initially we have the amorphous type of the solid being formed, right. As in the structure, there is no particular structure, right, and later on you are going to have the more stable forms, right. More stable form obviously are the crystalline forms, right, where I believe you can have, or the X-ray diffraction patterns are visible. So anyway, crystalline forms, you have, what do we say, I guess, a repeatable structure or a certain kind of a structure, right. So amorphous, you don't see that there though. So initially you will have the amorphous form, which is the most soluble, right, but is it the most stable form? No, not really. So the next stage would be the soluble crystalline form, and the last stage would be the most insoluble or least soluble crystalline form, and that is what we are looking at here, right. So obviously the concentration of the relevant metal keeps on decreasing, right, and initially the metastable equilibrium with respect to the amorphous solid, and then again the next stage. So this is with respect to a lapse in time, right, this is what the nomenclature means. So after again considerable amount of time, after passage of considerable time, you are going to have the next stage of metastable equilibrium, which is the soluble crystalline form, but at time equal to not infinity, I guess, considerable time. That is when you are going to have the true or truly stable form, or the equilibrium form, right, a true equilibrium being reached, and that's where it will be truly stable, right. So obviously you need to identify where you are at, as in the amorphous stage or soluble crystalline stage or such, right, and why is that? Because you need to know the log K values, right. So let us move on to see where we are at. So obviously here I want to know when is the the precipitation going to go through, and if it is going to go through, at what rate is it going to go through. So obviously in that case we are going to look at or consider this particular variable called the saturation ratio. So I am going to call that S is equal to Q by K solubility constant or solubility product, let us say, to the power of 1 by X, right. And Q, what is Q? You know that it is your ion activity product, right, and that is something we discussed in great detail in your what is it now, equilibrium related aspects, right. Again, if A plus B are in equilibrium with C plus D, what is Q? Q is nothing but the concentration, or in this case I am approximating concentration to be equal to activity, concentration of the products raised to the stoichiometric coefficient by the same case with respect to the reactants, but obviously this is not at equilibrium. So if the system is at equilibrium, obviously what will that be equal to? Q will be equal to the equilibrium constant, right. Anyway, Q is the ion activity product, which we discussed earlier. I am just trying to refresh your memory because it has been quite some time. Anyway, so you can get these values too. But what is X? X is the number of ions, let us say, as in for example CaCO3, right, the X will be equal to 2, and for AlOH thrice X is equal to 4. Again, why is that? Ca 2 plus and CO3 2 minus, so 2 ions, and Al 3 plus and 3 OH minus, so that is why 4 ions. So X is equal to 2 in 4 in this case, and X equal to 2 in this case. So you have different what do we say levels of S. So more or less what are you trying to do? You are trying to compare Q. Q gives you an idea about or snapshot about the current picture, with KSO, which is the picture at equilibrium, right. So Q is the current picture, KSO is the picture at equilibrium, and you are obviously trying to compare those aspects. So how will that help me? I guess it is going to define feasibility of my precipitation, right. And how can I look at that in general in vague terms? So when S is equal to 1, what does that mean? It is at equilibrium, right. When S equal to 1, when is that? When Q equal to KSO. So that is when it is at equilibrium. So for example, for this particular case, when is the system at equilibrium? Let us say CaCO3 solid, Ca2 plus CO3 2 minus, right. So when is it at equilibrium? When the solution is saturated. Right. And the second case, when S is greater than 1, right. This is the case when precipitation is feasible, right. Consider this when Q is greater than KSO, right. And what does Q greater than KSO mean? It is oversaturated, right. And obviously the next case, when S is less than 1 and precipitation is not feasible, or dissolution is feasible, I guess. What does that mean? That Q is less than KSO, right? And Q is less than KSO. What does that mean now? So Ca2 plus and CO3 2 minus can dissolve, as in the solid can transform into or dissolve into Ca2 plus and CO3 2 minus. And what does that mean? It means it's under saturated, right? So again, you can have the saturation ratios depending upon calculating the Q value or the ion activity product, right? So once you calculate that, you can know is it undersaturated or oversaturated, and obviously if it's undersaturated, the solid moving to the or dissolving would be feasible, and if it's oversaturated, obviously what is it now? The precipitation is going to be feasible, right? So let's look at what we are going to discuss next. So earlier we talked about some aspects as in stages in formation of a solid, right? So a solid as in, you know, you're not going to start with, let's say you just dump or increase the concentration of your relevant compounds. It doesn't mean you are going to immediately have or end up with particles of considerable size, let's say. As in I say considerable, it's all relative, right? Initially it's not the size of the particles that are formed initially are not visible probably to the naked eye unless they start agglomerating together. Again, we see those aspects here. So let's just briefly look at what are these aspects here. We have nucleation, right? So this is the process in which solid is formed from initially from only the soluble species, right? So again, process in which the solid is initially formed from only the soluble species, that's nucleation, right? Crystal growth, again, that's self-explanatory. Agglomeration is in general when you have, what do we say, increase in particle size, right? Ripening is in when you have change in the type of solid to more insoluble phases, right? Either due to the change in structure or due to the change in your particular, what is it now, size of your particle. Again, we are going to discuss all these aspects in detail. So initially for precipitation you are going to have nucleation. The next step would be crystal growth, right, growth of the crystal, and then increase in particle size. With agglomeration you have agglomeration, and then you have ripening, right, ripening of your fruit. Again here I guess it's not a good corollary here, right, but again ripening here, right. So let's look at each of these processes in greater detail. I guess we only have time for nucleation, so let's just discuss that for now. And we are going to say what is nucleation now. It's a process in which solid is initially formed. Anyway, obviously nucleation is the first step in your precipitation, right. So for the precipitation to go through, you first need to have nucleation, right. So obviously these nuclei, as we are calling, are the smallest possible forms of the solid, right. Anyway, process in which the solid is initially formed from soluble species, right. Again, as we said, this is the initial step or the trigger that's required for precipitation to go through. Obviously, what are the relevant conditions that are required now? You need oversaturation. So we are going to look at how to quantify that, or why we need oversaturation. I guess we'll look at that again in a few moments, right. Again, we initially need to have formation of this the initial the tiniest possible solids that we can call them before we call them as solid, and they are called, let's say, nuclei in this case, right. So we call that step the nucleation, I guess, and we need to form nuclei initially, or we need to promote conditions such that you form these nuclei, I guess. So obviously what are the different kinds, I guess. So here we have homogeneous, and we also have heterogeneous. So again, think of this as in homogeneous, as in you have nucleation. Let's say I have a beaker, or let's say any control volume, let's say, and I have the nucleation occurring throughout the particular what is it now, control volume at the same rates, let's say, right. So that usually doesn't occur. Why is that now? Because for nucleation to occur, you need very high levels of saturation, right. So for your particular solution to be oversaturated over the entire control volume, you need to have a very high concentrations of your relevant what do we say, cations and your anions, right. So that's usually not the case that it occurs. So in general heterogeneous, and that's what you see in nature, I guess. Where is it that your particular precipitation occurs first, let's say. So you have heterogeneous systems, right, as in you might have noticed that when you are boiling water or such, over time, where is it that you obviously observe more and more precipitation on the sides, let's say, or on the surface. Where is that? Because that's where you end up having, let's say, your initial nuclei being formed. Why is that again? Because you need a surface, right? For nuclei to be formed initially, we are going to look at that again. Gibbs energy change required for, or delta G required for formation of the surface, let's say. Again, at the surface are those heterogeneous layers or zones where you have high saturated concentrations. As in, let's say, this is my control volume. So for precipitation to occur throughout, so throughout the control volume I need S to be very high, right? But that's not always feasible. But let's say I have particular zones, let's say cracks or such, right, where the S is high, let's say, right. So the precipitation can start in this particular zone, right, where the saturation ratio is relatively high, but not in the bulk solution where the saturation ratio is still relatively low, right. So again, difference between homogeneous and heterogeneous, I guess. So that obviously again depends upon how you want to promote precipitation if you want to look at. So the next stage obviously is the rate at which this nucleation occurs, right, because that's the key again. If it takes too long, way too long, it's not feasible for me. So I need to look at, how do I promote nucleation or such. So I need to know what are the factors it depends upon. So here I guess the rate of nucleation is going to be equal to, let's say, a rate constant and S minus 1 times m. I believe this is empirical, and m can vary from 3 to 8, I believe, right, 3 to 8, yes. So what does this mean for you, let's say, for you, or for a guy who is trying to promote precipitation now? So K, it's a constant, right, R is the rate of nucleation. So we say that in this particular case for nucleation the rate is K times S minus 1 to the power of m, but keep in mind that m is 3 to 8. So S is the saturation ratio, right. So when did we say precipitation was feasible? When S is greater than 1, right. That is what I believe we discussed in this case, right. When S is greater than 1, precipitation is feasible, or when it is oversaturated, as in Q and KSO, right. But just because Q greater than KSO and S, let's say, is 1.5, let's say, or 1.1. So here it say 1.5 minus 1 times 3 and such, does that lead to considerable rates of nucleation? No. So what it more or less translates to is, for nucleation to occur, you initially need to have remarkably high concentrations of, or remarkably oversaturated solutions, right, as in S needs to be around 100 or 1000, right, and that is what you can observe from the equation 2 for this particular rate of nucleation to be relevant, I guess, right. Otherwise, if it is just oversaturated or slightly oversaturated, as you see, the rates are going to be relatively less. But because m, right, is from 3 to 8, so it is like a trigger, I guess. Once you have relevant high concentrations of the relevant compounds, or when your solution is relatively very oversaturated, because m is 3 to 8, the order is relatively high. So once you create those conditions, the rate of nucleation is going to be very fast. But to create that particular scenario, you need to obviously have very high concentrations of your relevant compounds for you to create high S values of 100 or 1000 or so on, right. So but once you reach that value, the rate is going to be remarkably fast again. So with that, I am going to end today's session, and then we are going to talk about crystal growth and the relevant kinetics there, and then I believe agglomeration and ripening and so on, and then move on to the equilibrium models. And so with that, I am done for this session, and thank you.